Good afternoon, everybody. So today's lecture is on sound quality, and a few aspects of sound quality have been discussed or a little bit mentioned in some of the few lectures on acoustics in the very beginning of the course. So before I begin with the description of sound quality, I want to differentiate that what is noise and what is sound. Noise in general, how do we define which sound should be characterized as a sound and a noise? Mainly because the noise needs to be controlled and the sound needs to be enhanced. So noise is basically the unwanted or the unpleasant sound which is measured mainly to avoid human annoyance, to fulfill the noise control regulations, and it is usually measured using A-weighted decibels, sound power, sound intensity, source strength. So we have already discussed many of these metrics on how to calculate the total sound level, the intensity level and other. But sound in general is, as you already be familiar, it is the fluctuation of the pressure variations which is perceived by the human ear as sound. So this is a very important source of information. It is informative sometimes. For example, in a musical concert, do you really want to reduce the noise of the guitar? No, you want to enhance it. So it is pleasant to you. In the same way, suppose in a classroom, for example, in this classroom, I definitely don't want a noise control near my microphone because I'm going to deliver a speech, a lecture, and you want to hear it. So certain sounds need to be enhanced, and that's where the concept of sound quality comes in. So the textbook definition of sound quality is the perceptual reaction to the sound of a product which reflects the listener's reaction to how acceptable the sound of that product is. So this term came mainly from the description of a product. So how desirable do a customer or does a user find the sound of that product? For example, for a driver, they may not like certain sounds, they may like certain sounds better. So what sound, for example, for a driver inside a car, the sound quality would be something where the sound is giving the information about the operational conditions of the product. So you can know that yes, my car is running smooth, it's working properly. So, and as you know, the definition itself involves that how humans perceive and judge the sound. So it is very subjective and it depends on, and usually it is measured through jury evaluations where we have a set of listeners who listen to the sound of the product and then they rate it on some set subjective attributes such as how powerful, pleasant, annoying, refined, sporty, luxurious, various adjectives. Like refined, sporty can be used for car sounds. Annoying is mainly for community noise or traffic related noise. So the same car sound which was informative to a driver now becomes a source of noise for the residents who are living beside the traffic, very high traffic area. So as Professor Bolton pointed out today, that how we perceive sound or what becomes a noise is very much dependent on the state of the listener, as in what state of the listener is, whether he is going to use that product or whether this product is external to him and for him it's a noise. And we'll study in detail how these metrics are defined in our later slides. But as I said, we are engineers. So no matter, how subjective a human perception of the sound is, to make our things easier, we engineers want to define everything with numbers. So if we can have some objective numbers through which we can say, okay, if suppose the loudness level of the sound is this much, then it will be perceived as much better for a sporty car. So we want to define everything by numbers. So some metrics which are called as sound quality metrics or psychoacoustic metrics, they have been devised which correlate very well with how the human ear receives, analyzes and perceives the sound. So the core of the sound quality research is to make design changes or to apply some acoustic treatments to a product to overall enhance the quality of the sound. And how this is achieved, we either there's two ways to go. Either you measure the sound quality metrics, you try to then make some design changes to improve these metrics, and then you subsequently conduct a jury evaluation and see whether it's actually affecting. So we'll go one by one with these things. But firstly, why improve sound quality? So as already pointed out, the better the sound quality, the more desirable a product is, the more it's going to sell in the market. Just like and the most common example that I'll be giving in this lecture is related to cars and automotives. In a car magazine, for example, when you have various parameters like the horsepower of the car, the engine cubic capacity, sometimes the color or the body shape of the car, the visual aspect. In the same way, the sound quality has also become one of the important product parameters. And as I already said, that it is useful for giving the operation conditions of a vehicle. To demonstrate how sound is very important to a brand, for example, different brands these days, they focus on having a unique sound. A manufacturer of Porsche does not want to sound similar to a BMW. A BMW manufacturer would not want to sound similar to any other brand like Jaguar, Tata, any other brand. And I have some sounds where I have some sounds from their respective websites, and where they have specifically mentioned that please see the engine sound or the pass-by sound, and our aim is to make it more powerful and more refined. That's what was mentioned in the website. So if, for example, BMW sound, according to these manufacturers, they want to sound more powerful. A car that has a very good pickup, so they want to sound more powerful. And similarly, Porsche. So sound can vary from brand to brand, and within the brand from model to model. Definitely a Formula car will try to have a different sound quality than a premium car. So for example, if we play this Porsche, so this is one of the car, and this is. So the second one is more smooth and more like it's like a more premium family car. The other one is more powerful. So different brands now want to have their unique signatures in terms of the type of sound they have. So sound quality is a very attractive feature of the product, and it makes it more desirable. And within the NVH design of any industry, sound quality engineering has become an important aspect, where the definition is that we try to tailor and enhance a product so that we improve its sound quality to enhance the experience of the customers. How acceptable the customers find, what is to enhance the experience. So for example, within a car, the aim would be to reduce all the annoying sound, all the tonal sounds, but at the same time enhance certain characteristics which make it sound more powerful. The process of sound quality engineering, it's a cyclical process. So what happens that within this program, suppose we have a product, then the first part is capturing the sound of the product, and then conducting either listening tests or using the sound quality analysis program, where we use different metrics. We calculate that, we do some time and frequency domain analysis, and the main aim is to correlate these metrics with subjective hearing. So in a standard noise control program, what happens is that sound is measured. For example, the decibels of the sound or the A-weighted decibels of the sound is measured, and then we see that if we reduce these decibels, are the people, for example the residents near a traffic area, more happy? Is the annoyance reduced? So that becomes a noise control strategy. In the same way, for sound quality engineering, the strategy is that we, for example, we vary the different metrics which are not only the decibels but also like A-weighted decibels, loudness, sharpness, roughness, fluctuation. And what these metrics are, I'll be discussing them individually, but these are the commonly used psychoacoustic or sound quality metrics. So these the aim now becomes not just to reduce the decibels, the aim now becomes to manipulate or change the other sound quality metrics, and then we see that okay, we have changed it, we have improved the sound quality. Does it correlate with how the users are perceiving it? So we can conduct a listening test, and this is a cyclical process. So based on that, some troubleshooting, and then again back to the product engineering design. So within the design phase itself, if this thing is done, then the design changes can be made to improve the sound quality. So the first part, as I said, within this cycle, it's sound recording, then analysis of the sound quality, and subjective test. And these three parts are the ones that I'm going to discuss in more detail in this lecture. Sound recording. Now the technique used especially in sound quality engineering for recording sound is called as binaural recording technique, where we use a head and torso simulator. So here in this figure you can see it's a torso, and at each ear we have a microphone, and when you go to the lab for lab tour, you will see this head and torso simulator in our acoustics and condition monitoring laboratory, and how it's used to capture the sound. So the idea is that, suppose we have the idea here is that suppose there is a listener, and this is the left ear and the right ear, and this is suppose a sound source somewhere here. If the head was not present, instead if there was just a source and the same left ear and the right ear, so we have just a microphone placed at near the location of the left ear and a microphone placed near the location of the right ear, and we do the 2-channel recording, and then we play the 2-channel recording. Now instead of these 2 microphones, we also have an additional upper torso and the head. Then this technique becomes more effective. Sorry for my drawing, but this technique becomes more effective. And what is it? What makes the changes is that, see, now we have an object here, we have the head. So what happens is that when the same sound is hitting this left ear, and then it is hitting the right ear, and suppose a vehicle is passing by from here, then the sound is not directly coming here, instead it's going around here. So we have the geometry of the head, we have the nasal cavity, we have the mouth cavity, and the sound is bouncing back, it's reflecting, it's going through these cavities, and finally it's warping around. Many effects happen, and then finally it reaches the right ear. So just placing 2 microphones spatially or placing them with a head and torso will be different. This will capture the spatial information much better. So that's the technique we use, and when that same sound which is captured through this torso and is played over, then a listener can actually feel the difference. You can actually feel that it very well captures the direction of the sound, and you can very well say that okay, this car is approaching from my left, right, or from the right position, or the left, or from so and so degrees from the right. So it very well captures the direction of the sound. So that technique is used to capture the sound. And now I'll come to the sound quality analysis part. Suppose there was a damaged product or there was a new product, and the binaural recordings are taken, or the sound of that is recorded. Now what kind of analysis is usually done? Now again I said that the objective of an engineer is that no matter how much of human aspect or how many other variables, external variables be there, we want to have some numbers to play with. We want to rate using some numbers. We want some numbers. So and human hearing, as already pointed out in some of the previous lecture, that a microphone is a linear system. but the human ear is not. It's not like a microphone, it's not a linear system. So if we studied in a microphone that this is, for example, the response characteristic of a microphone, and this is the fundamental frequency, then usually this becomes the operating range where we have a flat response. So if a 10 dB sound is played, if a 10 dB sound is being recorded from the microphone, then it is recorded as 10 dB and not as a higher decibel, somewhere here like 20 or 40, 70. So we want a flat linear response. So most of our transducers, they are designed to have a linear response, but our human ear does not. What happens with the human ear is that if instead of microphone we have this human ear and the sound is passed, then based on what frequency of the sound is, it varies. So some metrics have been defined to capture this frequency filtering of the human ear, and these are called as sound quality metrics or psychoacoustic metrics. Psychoacoustic, why? Because these are actually the acoustic metrics. We measure the sound pressure and then we apply a frequency filter to get these metrics. So these are acoustic metrics, but because of the human part on how well it relates to human hearing, it's called psychoacoustic metrics. And the most commonly used metrics are A-weighted level, loudness, sharpness, roughness, and fluctuation strength. There are others as well, but I am only going to discuss the most common ones. So now this is the human ear. I think in our first lecture, Professor Bolton was telling us that when when the sound falls on the human ear, then there's an organ that equalizes the atmospheric pressure, so that only because the acoustic pressure is not the atmospheric pressure, it is that small change in the atmospheric pressure or that small fluctuation, which even 1 Pascal can be equivalent to 94 decibels. So this small change, this fluctuation is the one that needs to be captured by the human ear, and that is done by this particular thing that's called the Eustachian tube. So this is the pressure equalizer. So after the sound comes and is collected in this outer ear, it passes through the ear canal, and then from this tube, this acts more or less like a pressure equalizer. And without going out of scope with because this is not a class of anatomy, so I can only discuss the acoustic part of the human hearing. So this equalizes the atmospheric pressure, and finally, so this is the the tube where it passes, and then finally only the pressure fluctuations go through this tube, and this is called as the cochlea. For sound quality and for psychoacoustic, it is a very important organ, because this is the organ which is the human filter, the human frequency filter. So what happens is that when the same sound that was passing, so here we have the flat response, from here we have the flat frequency response, so the air fluctuations, they are passing through, and finally it enters this spiral cavity, the spiral duct, and the air vibrations, there's a fluid filled inside the cochlea, they vibrate the fluid within the cochlea, and then at the end we have a membrane that is called as the basilar membrane. So how it works is that when the sound fluid, this is the fluid inside the cochlea, it winds up and then it hits this basilar membrane, that's the end of the cochlea. And from here we have the hair cells which convert, in the microphone, what is a diaphragm? It is equivalent to the human diaphragm. So finally the vibrations of this membrane are captured by the hair cells, which is converted into the electric signals that goes through the neurons and reaches a brain. So the very unique characteristic of this basilar membrane is that different frequencies, they activate or they stimulate different parts of the membrane. So we have this membrane, different frequency sounds hit different parts of this membrane, and different parts generate different vibrations. So no matter whether the level is same, but because it's hitting a different part, it's generating a different vibration. So the response becomes non-linear. And after many studies that were done on humans, on the hearing of the humans, subjective test, this equal loudness contours were developed. So this is a curve that shows that this is the frequency, this is the decibels. A flat response would be something like this. So for every, if this that 60 dB sound at this frequency should be 60 dB, but this is the loudness contour of a human ear, which means that these are the loudness expressed in the unit called phones. So the same 60 dB sound at a frequencies near 1000 hertz, that same 60 dB sound is the human ear is more sensitive to this range. So for example, a 20 phone sound will correspond to 20 dBs. So 20 dBs gives 20 loudness, 60 dBs are giving 60 loudness. But that same 60 dB, if you trace, then as you go backwards towards these frequencies, lower frequencies, then it corresponds to lower loudness. So that same 60 dB, these are various loudness curves. Then suppose it corresponds to 60 dB, in this is the most sensitive range. Then in these range, it will correspond to a much lower loudness. So overall the sounds in these regions are attenuated. The sounds here, the human ear is more sensitive, and again the sounds are attenuated here, and these curves are these curves are the curves of equal loudness, how the equal loudness of the human ear perception. So this is again the equal loudness curve. This is the threshold of hearing, this is the threshold of pain. And I remember one of our participants asked that how loud a sound is, how loud a sound can we hear, and how loud. So we our human ear also has a limitation, and the hair cells do get damaged after a certain amount of sound, and this is the threshold of pain. It's almost similar to 140 dBs near the 1 kilohertz zone. And this is the threshold of quiet or threshold of hearing. This is the absolute threshold of hearing, which means that if there was no background sound and there was a healthy human ear with no impairment, and usually threshold increases with the age. So if it was a young human ear, healthy, then in the absence of any sound, what's the minimum sound it can hear? So this is the threshold of pain, which is 0 dB. That was pointed out in the lecture. So I would like to, in the previous lecture it was pointed out, but I would like to say that no, it's not 0 dB. If we have a pure tone of 1 kilohertz, it's 0 dB, but as you see, for different frequencies it changes, because our human ear is more sensitive here. But even, for example, at 50 hertz, it's a 50 dB sound that we can first hear. Okay, so now now that we have understood how a human ear works, we'll go to what metrics capture this human hearing. And these are the metrics that are used for improving the sound quality of a product. The first is the A-weighted decibel. This is a curve, this is the filter. So this factor is applied to it. So what happens is that this gives the A weighting factor. This is the formula. It gives the A weighting factor, and this A weighting factor is applied at the various frequencies. And the total LA equivalent, if it is represented in the narrow octave bands, then this is how the total equivalent level is calculated. So first the sound spectrum is represented as a dB spectrum. So the frequency response is the frequency spectrum of a sound is calculated. Then we apply this filter and we get that in A weighting. I would just like to point out that this corresponds to the A weighted curve of a 60 dB sound. It hasn't been mentioned here, but this corresponds to the 60 dB sound. Okay, so at 1 kilohertz is 60, and then as we move further down, these are the weighting factors. So there is a reduction that happens at lower frequencies and at these frequencies. So as you can see that from the equal loudness contour, this is almost like a inverse of this. So what we do is that if we trace this, so if we trace that, okay, a 60 dB sound at 1 Hertz, a 60 dB sound at 2 Hertz, a 60 dB sound at 10 Hertz, 20 Hertz, what will it correspond to in loudness? If we trace this throughout, then what you get is that same 60 dB sound, when it is for a human ear, based on many years of research, we have found is that for a human ear, that same 60 dB, a broadband 60 dB sound, for example, when it is passed through the human filter, this is the equal loudness. This is how we perceive. So this becomes it changes, the human ear changes this curve to this one, and this is the A-weighted curve. So A-weighted curve is very similar to the human ear response. So that is why mostly for noise control, the environmental noise control, dBA is considered as a much better weighting compared to decibels, as it correlates more with how we hear it. Okay. Another concept in the sound quality or psychoacoustics is the critical bands and bark scale. This is we have a linear frequency band. This is the linear frequency scale, for example, 1 Hertz, 2 Hertz, 3 Hertz, so on so. So linear. Here in the linear scale, what happens is that if suppose we have this is 10 Hertz and this is 20 Hertz, and we have these equal distances, so every distance is now 20 Hertz. This is the linear scale, but that's not how a human ear perceives it. So in a human ear, as I said, that different frequencies, they activate different part, and that is why they create different level of vibrations. So a critical band, so for sound quality calculation, we use this we represent the linear frequency scale into a bark scale, and the bands, the individual bands within this bark scale are called as the critical bands. So what happens is that within that individual band, the definition is that these are those frequencies which activate the same part of the membrane of the human ear, the basilar membrane of the human ear. So when we have the individual frequencies within this, so they activate the same part, so obviously their response will be similar. So these bands will give similar responses, and if two different tones within this band, they are played together, then a phenomenon called masking happens. And I just a point of caution here that this masking is not sound masking, which is something which is done in noise control, active noise control, where there is a sound already there and then another sound with a negative amplitude is played over that masks it, and overall the amplitude becomes less or zero. So this is not sound masking, this is auditory masking, which means that if two sounds, two pure tones, for example, are played at frequency F1 and frequency F2, then these two cannot be distinguished individually when they are played together. They will sound similar to us. Only after a certain difference can we distinguish them. So this critical band corresponds to those bands which sound similar, which our human ear cannot distinguish. So this is the minimum band, and the bark scale is the scale of the human, and this is the scale from 0 to 24 barks, which corresponds to the different bands. I mean, this is the representation of the human auditory filter. So it represents the frequency resolution of the human ear. For people who are interested, they can always look up the values. Okay, now we'll come to, so we have already discussed about the A-weighted decibel levels. The second metric is loudness, and the reason why I described critical band and bark scale is that these metrics are calculated using the critical band and the bark scale. So the frequency, the linear frequency scale is first converted into the bark scale, that's a non-linear frequency scale. And loudness, now all the sound quality metrics, the names are according to how a human ear perceives it. So the loudness simply is a correlate of how loud the sound is to a human ear, and it's calculated using this formula. So what happens is, this is the formula. So what happens is that we already know the equal loudness curve. So from that we can get the specific loudness curve in phones. So this, so suppose these are all part of signal processing. So if a 60 dB, for example, a broadband 60 dB sound is passed through it, it is first converted into the specific loudness curve, which is calculated from the equal loudness contours that I discussed in our previous slides. And then the linear frequency scale is converted to Bach scale, with every individual band is a critical band. So finally, this is, the scale is changed here, and that filter is applied to come to the specific loudness curve. And the area, so this gives us the specific loudness, which means that at so and so frequency or so and so critical band, this will be the loudness. So and so frequency, this will be the loudness. So it's the specific loudness at individual frequencies. And so the total loudness of that 60 dB sound would actually become, so from the previous formula that I had, it's the area within the curve. So it is the area within the curve. So this is the total loudness. So this is how the loudness calculation is done. So the same 60 dB sound, the broadband 60 dB sound, has now become 19.5 sones, which is the SI unit of loudness. The next sound quality metrics is sharpness, and this is the human correlate of how sharp you find the sound, or how high pitched, how sharp. For example, a female voice and a male voice, they are both speaking at the same level, but the female voice will be sharper compared to a male voice. So that's the sharpness. And the unit is accoms, and this is the formula for calculating the sharpness. So again, for sharpness also, we first calculate the curve of specific loudness. This n dash is the specific loudness, which we had calculated in our previous slides. This is the specific loudness curve. Anyway, so we calculate that, and because for sharpness, the higher the frequency content of the sound, the sharper the sound is. So we apply a frequency dependent function, so where we apply more weighting to higher frequencies, lesser weighting to lower frequencies, and we apply this to the specific loudness curve, and then we divide it by the total loudness of the sound. So we get a fractional value of small value, which usually varies between 0 to 2, and we get this sharpness. The third metric is called fluctuation strength. This is about what is the loudness modulation at low frequencies. So how modulated the sound is, how fluctuating, as you say, fluctuation strength. So to a human ear, how fluctuating the sound is, how much fluctuation strength it has. So if suppose we have a wavefront, this is the actual wavefront, suppose, something like this. But we need to find out that for a human ear, if just like we have the auditory masking for frequencies, so the frequencies which are very close by cannot be distinguished individually. In the same way, we have a temporal masking which is in the time domain. So two sound signals at time t1 and at time t2, when they are very close spaced. So suppose we have two loud bursts together, and there may be very fraction of seconds of difference, or only few seconds difference, but to a human ear it may sound like a single burst, or it may sound like they may not be able to hear it as single sound burst. So if these are two sound bursts, but when they are close together, then masking happens and we hear it like this. This is how we hear it. So because of the masking, we cannot individually differentiate it. So when we have a sound, when we have a modulated sound, we first calculate the loudness level of the sound. So suppose this is the loudness curve of the sound. Then we calculate what is the masking curve, and this gives us the masking depth. And this formula is used to find out, this is the masking depth, and this formula is used to find out the fluctuation strength. the reference taken is 4 Hz, but it is for how the sound, the amplitude of the sound is modulated at below the frequencies of 20 Hz. And in the same way we have roughness, which is very, very similar to fluctuation strength, but roughness gives you the higher frequency amplitude modulation of a sound. So if a sound is amplitude modulated, then we take the frequencies between 15 to 30 Hz. So within that frequency, what's the modulation like? And within this lecture, I cannot go into the detailed description or the derivation of these equations, but it's more about how these metrics are applied in sound quality research. So I'm just giving you what these metrics mean, as in what they correlate to. For example, loudness correlates to the loudness, and the fluctuation to how fluctuated the sound is, and roughness to how rough or annoying a sound is, and how it's calculated from the sound signal. So first it's converted into critical band and then specific loudness curve, and then various processing is done. So how these metrics are calculated, and then once these metrics are calculated, how they are used for improving the sound quality. So these are the 4 metrics that I have discussed. I'll skip this because this is a part of our lab. So once we have calculated these objective metrics, then the other part is the subjective listening test, which is also called as the jury evaluation. So here the listeners, they are presented with different sounds, they rate the sounds, and then they judge the sound quality. So this is the stepwise. First for example, we have a product sound, we have an original sound, and then we have the modified sound, either modified by making some design changes, or modified by changing or manipulating with the sound quality metrics, and the edited sounds and the original sounds, different variety of sounds are played to the listeners. They judge or rate the sound on some standard perceptual dimensions, and then correlation is found, as in correlations, and then statistics is performed to find out, for example, that for example, a loudness level, an example result could be that the loudness level from 15 to 20 dB corresponds to a much higher customer perception of powerfulness of the product, loudness. And in most of the research, you will see, and automotive research, is that the loudness metric corresponds to the powerfulness of the car, and usually for heavy duty and for sports car, the loudness metric is enhanced. It needs to sound more loud, but roughness, especially, but similarly for a premium car or for a very family or a premium car, roughness needs to be reduced. So this analysis just gives you that what metrics or what metric values correlate with humans' judgment, and then we try to change or modify these values. So we apply either design changes or we apply some acoustic treatment and see whether this loudness is reduced, increased, roughness is enhanced. I had discussed in this lecture about binaural listening. That is a binaural recording technique where we have a head and torso simulator, and then we have 2 microphones, and it captures very well the spatial and the directivity of the sound. That same sound can then be played through binaural headphones, or it can be played through a speaker array, and people can listen to that sound and they can rate it. Now how they rate it is a slightly this concept is little not related to acoustics, so I would briefly describe it, but it's not related to acoustics. But the measures that I used, studies show that for example, that is a product sound, then usually researchers find out that what are the adjectives or descriptors that listeners use to describe that product sound. And all this research has already been done, so we already know what metrics what dimensions to use. But usually the way it was calculated is that a large number of listeners were played a product sound. For example, a car sound. Many listening tests were performed, and the listeners, they listened to different types of car sounds, and they used various words like powerful, quiet, refined, sporty, luxurious. So a wide variety of car sounds was played, and we found out that what are the words that are most commonly used by people to describe the character of a car sound. And then using techniques such as factor analysis, principal component analysis, the words that are used, they were clustered or grouped together to find out an equivalent of a coordinate system. For example, in mathematics, for example, the location of a point is given by the coordinate system of x, y, z and t, the x, y, z coordinate and the time coordinate. In the same way, for describing the sound quality, they wanted to come up with a coordinate system. So what they have is that they have two orthogonal dimensions, and for automotive sounds, from research it has been found that we don't need to ask people, okay, how luxurious, how sporty, or how, we don't need to ask so many things. If we just want to rate the sound of any car, we can just ask them about two individual things. For example, what is the strength? The first scale measures, the first dimension measures the strength or the power of the car, and the other one measures the comfort or the pleasantness aspect of the car. So just by measuring these two, almost any car can be defined, and this coordinate system then becomes a way to distinguish different types of products. For example, this could be car brand A. The sounds of the car brand A are somewhere here, and suppose we want to improve the sound quality, then these sounds from here needs to go up till a higher place where they are perceived as more powerful as well as more pleasant. So this is how to make the task of subjective judgment easier, we ask the customers, okay, this is how we have a new product that is making, and it's been designed, and this is how the sound is. Then they can listen to the sound and they just rate it on these two aspects, and based on this we can characterize that, okay, this is the sound quality on the subjective, and we already know the objective metrics, and now we know how the subjective, where does it fall within the subjective space, where does it fall, and then we can correlate. Okay, so for a car, for example, I've already told you that for a premium car, as I told you, what has already been found from research is that roughness, if roughness is reduced, then this subjective judgment goes up. If the loudness of a car is increased to a certain extent, then also the perceived loud powerfulness and pleasantness goes up. But after the loudness is increased further, the powerfulness will go up, but the comfort or the pleasantness will decrease. So we try to use numbers to define how humans find the sound. The overall idea is to define some metrics. So instead of using decibels, in addition to using decibels, using other such values like A-weighted decibels, loudness, sharpness, etc. to define the character of a sound. And then we can use these are the scales that I used. So the overall process is that once we know that we have done for example, this is a product, the sound quality analysis is performed, and then some noise source identification technique is used on this to find out what are the major noise sources. And we now know that, okay, this is we know that how loud, how rough, how sharp it is, and how people find it. Then a design change can be made to the major noise sources to reduce certain characteristics which people find undesirable. Okay, now I'll briefly introduce you to a small application of the sound quality research, which is still very new and very few people have done. But this is something we have been doing in our lab, is how to use sound quality for fault diagnosis. Now, it is quite intuitive that sound quality, which means that how people are finding a product. So obviously it gives you information about the operation of a product. So obviously a malfunctioning product will sound different. It will, its quality to us, its quality will decrease. We will find it as not good. So its quality will decrease. So can we use the objective metrics to understand? Can we use these objective metrics to determine whether a fault has occurred within a system? So what we did, that we have an engine test simulator that is run on a dynamometer, and in the lab tour you can get to see this engine test simulator. So it was run on various load torques and RPMs, and the misfiring conditions were created, and the sound was measured near the engine, exhaust, and the vibration signals were also acquired. So this is a typical example of fired and misfired engine. So if I play this, for example, this is the signal at 20 Newton meter and 2100 RPM, and this is at the 1260 RPM. So as you can see from the wavefront here itself, you can identify the misfired, when the misfiring happened, when did the engine start misfiring. But here it's very difficult to identify. So when you play this one, this is how it sounds like. And as you see, just by listening itself, you can know that okay, there has been a change. Maybe the engine has misfired or something has occurred within the product. But here from the wavefront, we cannot tell. But when you listen to it, our human ear can understand. So although from the wavefront we are not able to distinguish, but from the human ear you can understand. I'll play it again because it's not. I'll just play it again. So this is when the engine is running with all the cylinders properly, and then suddenly one of the cylinders misfires, and suddenly you can see that although from the wavefront you cannot distinguish, and then we calculated the dB spectrum, we calculated the decibel levels, there was not much difference in this condition. There was a marked difference here but not here. But from hearing we could understand that it has misfired. So we saw, what we found it is that it was the loudness, the fluctuation and the roughness which actually correlated very well, and we could predict a misfiring condition with 90% accuracy. So this is just one of a potential application for sound quality. So in addition to the sound quality research to enhance the customer experience and to improve the overall desirability of a product, we can also use it for fault diagnosis. And with this, these are a few references that I had used throughout my lecture slides, but with this I would like to conclude my lecture and I would open it for questions.
Level of the sound, how much of a duration you are allowed to withstand that without creating a permanent damage with your human hearings, because no matter what we do, God has given us a nice pair of ears, let us protect it, okay, and that's the best we can do with our ears. We may be, that is the reason why we do noise control. I told you right in the beginning, noise control is there just to protect ourselves first. If you look at an energy point of view, I must mention to you, those of you who would have done heat balance on IC engines, we try to always measure what is the input energy to an engine, and then we see a heat balance, like this is the power output of an engine, and this is the power taken out by the cooling system and by the losses in the engine because of the friction, etc. But we never do what is the energy taken away by the acoustical noise, because of the fact this energy is very negligible. Okay. So engines make noise, but we never consider that because from an energy point of view they are insignificant, but from our ears point of view they are very, very significant, and that is why it is very important to us. So we all know we live in an atmosphere or in an environment where noise is being produced because of different functions happening in our neighborhood, in the environment, by us, by the neighbors, everywhere. So, and we would not like to live with noise. Okay. So, noise pollution is a concern for modern developments. In fact, I recall about 15 years ago when we were developing on our campus, I had a couple of undergraduates doing a project with me. So, I gave them a pretty new sound level meter and asked them, every weekend for a few weekends, measure the noise at different times in and around the campus. That was 15 years ago. And then again we did that also recently, and you will see the noise levels around the campus growing up with time. That is because we are developing. People are growing, flats are coming up, businesses are opening, and that is true for the entire civilization. I recall, I do not remember though, in one of these inter-noise conferences, one gentleman showed us the map of the world with the noise levels recorded a few years ago and what it is at present, and they could see throughout the globe this is a global phenomenon. Everywhere noise is increasing. Well, that's a good sign because we are all progressing, we all are constructing, we all are having highways, airports, and commercial establishments coming up. That's a sign of civilization, but that's fine. But that does not mean that we should not care about the noise levels. In India particularly, I am sure in every city now we have this metro constructions coming up, highways coming up, skyscrapers coming up, and so on. The construction equipment, metro noise, everything is adding to the community noise. Okay. And those of you who come from cities, we live in a quiet campus. It's nice. You can still hear the birds chirping in the middle of the night and in the morning. But if you go to the cities, these are rare things. You never are at peace, and that's why people who come to Kharagpur campus from the cities, they say, well, there's a nice resort. Okay, so that is why, because the noise levels, community noise levels are low. But then we have to be careful about that our ears are not exposed to high levels of noise for a prolonged time. So, well, what are the common types of environmental noise? Transportation, railways, roads, aircraft, ships, everything. More power means more noise, and sometimes people like noise. If you have seen the Indian people's driving on the road, horn is might give me way, give me a way. The drivers love to blast their horns and then make demand way from you. They think if I blast or make more noise, I have the right of way. But I remember when I was talking to the BMW dealer. I mean, the executives from BMW had come down, and the Indian driver was driving them in their BMW, and the drivers were always honking the horns on the roads of Calcutta. The executives are very unhappy. They told, our car should be recognized but just by its look, not by the driver blowing the horn. That's that's their marketing strategy. People should make way for a BMW just looking at it, not because it is blowing horns. So now this industrial buildings, factories, machineries, AC systems, HVAC systems is a big issue. Commercial establishments coming in shopping malls. So we have kitchens with the restaurants, etc. The kitchen machinery making noise, plant rooms in hotel making noise. So everything adds up. I mean, so you all can imagine if all these items which I had listed here were uncontrolled, how miserable our life would have been. Okay. Fortunately, there are regulations in place. And this is what I am going to tell you. What do we measure? How do we quantify so that the noise levels measured or produced are within the limits? Okay. And a big nuisance in India in few years ago was this firecrackers. We have a festival called Diwali, And as teenagers, kids, college kids, even we used to love bursting crackers. Okay, I would see in the neighborhood who makes the loudest noise. Okay, but then of course the government has stepped in, and they have put the control right at the manufacturing stage. That, and we'll come to that. That if a firecracker produces such and such level at such and such distance, you are not allowed to sell that. Okay, and things are pretty much in place and in control. So I will not go into the mechanism of hearing, but it only suffices to say that if this hair cells or the hairs inside your ear somewhere here, if they break, you have a permanent damage. And a doctor friend told me, if you are deaf, permanently deaf, it's irrecoverable. I mean, you cannot fix it by medicines or putting hearing aids. Okay, so one has to be very, very careful. And those hair cells, if they break, your nervous system is not connected to the outside cell, outside world rather. Okay. So, as you all know by now, our eardrum is a very thin membrane which vibrates because of this fluctuating pressure, and you know how this pressure equalization is being done. So, this is the small fluctuation of pressure behind which all our efforts in studying acoustics is. This small fluctuation of 1 Pascal is making our life terrible. So, just to recap, you all perhaps would be knowing by now, this logarithmic representation of the sound pressure level, because of the fact that the dynamic range is very high to represent in a linear scale. So, a decibel scale or a logarithmic scale is convenient to handle such large quantities. But I always caution my friends and students, never add decibels. Log m plus log n is not log m plus n. Okay, so please do not do that mistake. And many of the undergraduates, I am sure they know it, but they never do this. Okay, so this will mess it up. We do a lot of consulting for the industry, and I have been to places where we have with a lot of difficulty come down from a level reduced to 5 decibels. Okay, then the management says, why don't you reduce it further by another 5 decibels? They do not realize the pains taken in coming down further 5 downs, and then say, then when I demand that my charges are also in dB scale, then they get worried about the levels. So, 140 dB is something one has to be careful about. Okay, but then we have some idea of what this A weighting is, because as you know, our human ear is not a linear instrument, it is a nonlinear instrument, and this A weighting is nothing but a weighting function which we apply to the measured, something like this. Actually, it is 0 dB yet. This is the A weighting correction at 1K. So, if you weight it, we will get something like dBA, and unweighted is represented in dB. And those of you who are doing noise control engineering or noise control, sometimes if you see a number, say, I will just give an example, something is say 90 dB, okay, and it is 83 dBA. Looking at these two numbers, one can quickly say, well, the low frequency sources are very predominant in this kind of spectrum, because A weighting is pretty high, the minus values are pretty high in the low frequency ranges. So, A weighting would be less than the unweighted. So, whenever you see a dBA value less than the dB value, you can fairly say that the frequencies which are creating the noise are less than 1000 kilohertz. That is a thumb rule. If you do not have any filters also, you can keep that in mind. It works. So, perception of decibels. 5 dB or 10 dB. I've been to industries where the engineers are happy if you see a difference of 3 dB, but it really, when you do an A/B comparison, switch on, switch off, you can only notice a 3 dB difference. But to bring in any substantial difference, it has to be at least more than 5. And of course, we have been talking about audio frequency ranges from 20 to 20 kilohertz is our audio range, but things do happen beyond 20 kilohertz in the ultrasonics and infrasonics below 10 hertz, below 20 hertz. One has to be just aware of the frequency sources. And you all know the relationship between this wavelength and frequency. This is just recapping things, those who are joining us for the first time now. And we are talking about the audio frequency range. But some people are hard of hearing at high frequencies. As you go old, there's a problem here. And look at this auditory field. People have discussed this by now, but this is the lowest level which a human ear can hear. This is where we can subject our ear to, and if you look at this green patch here, speech and music. When human beings speak, this is predominantly the frequencies in which we produce the sound, and of course music could be produced in this range and so on. So there are many ways by which, if you look at this environmental noise, there are many issues with this. One is whether we are comfortable. By comfortable, I mean whether the noise levels to which we are exposed are such that we do not harm or damage our ears. Next is, am I able to communicate? To somebody who is in the surrounding. Okay, you would have seen the helicopter pilots. Okay, the chopper running always, they have a tough time communicating even in their headsets. So they always have this active headsets in them when they speak to people over the microphones. Perhaps your voice is going to get masked over the aircraft chopping, rotor chopping noise. But then in a classroom, in an auditorium, there are also measures to ensure that my speech quality or the way I communicate is being heard by others, and usually it is done through a voice modulation. And if you look at there are standards, the IEC standards, to measure what is known as the speech interference level. How do you quantify that your environment, be it a classroom, be it an auditorium, that it satisfies certain speech interference level criteria? Okay, and that can be measured, and the way it is done is a modulated source is produced at a source, and at a receiver it is received, and the modulation index is calculated to see whether the SIL is within a allowable value and so on. So this is something which, to classify rooms, people do that. Okay, because I imagine if this room was reverberating. Professor Bolton is going to talk about room acoustics tomorrow. Imagine this is a quiet room, and when I speak, you can hear me. Instead of, suppose this was a squash court, okay, or an indoor badminton court, you would not be able to hear me or understand me clearly because there would be multiple reflections. So a lot of room acoustics also comes into play for a better understanding of the speech quality somebody is producing. Okay, that's something we'll discuss later on. But environment, when I say environment, it is just not the environment does not mean something outside, outdoor field. It could be inside a room, inside a classroom, inside an auditorium, inside a vehicle. Okay. One has to be careful about all that noises inside your bedroom. I'll tell you another story. In India, we have a transformer manufacturer, electrical transformer manufacturer, and in Europe, they have this single phase transformers put on a pole in the residential neighborhood. And as you know, because of the electromagnetic forces in the transformer, they produce a humming noise, a 50 hertz or a 100 hertz humming noise. And in the middle of the night in a quiet neighborhood, if this transformer humming noise is being produced, people get disturbed in their sleep. Okay. So, the level were as low as 36 dB at a distance of 1 meter, and they were not fulfilling the Italian standard. This phenomena happened in Italy, and there is this company in India who had manufactured their entire lot of transformers got rejected, okay, because the transformers were generating humming noise which produces 36 decibel, which created nighttime sleeping disturbance to the European community, because the standards were pretty strict. I wish we had such standards in our country as well, but then there comes the role of the noise control engineer. How do I quieten a transformer which is producing a humming noise at 36 dB? Okay, that's a different story, how we control it, but I wanted to drive home the point that there are issues. We say sometimes 36 dB is so low. No, if I have to sell in that country, I have to ensure that this product satisfies their noise emission norms. And I am sure all of you are now familiar with automobiles pass-by noise. Today India is a hub, automobile hub of many auto manufacturers, wherein in our country we manufacture them and we export them to other countries. And of course, when we export to the other countries, for example, many companies in India, we manufacture and export in Europe, export in Southeast Asia. But then imagine if you are going on a road, there is a standard which is known as the pass-by noise measurements. So, there is an ISO standard for that. You can look up the ISO standards. This distance is about 50 meter, and on either side from 7.5 meter from the center of the road, you can put an SLM, and the vehicle is made to move here. Once it comes to point A, okay, in second gear, you are in wide open throttle. Okay, so the driver slams on the gas, okay, and goes to point B when he releases the gas. Okay, so what is the maximum sound level measured at this location C has to be less than a certain value. In India, and that is the pass-by noise levels. So, why did this come into being? Because imagine today, if the highways were there and everybody had big engines, and highways and buildings are coming up next to highways. Okay, imagine the situation if there was no control on this pass-by noise. What would be happening to persons staying inside the house? I remember, the first time I went to Mumbai, I had been to one of my friend's flat, and they were staying close to I should not name the place, but staying close to a track in Mumbai, and in the middle of the night, tak-tak, 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 that local trains going. Okay, it's irritating. Okay, I'm sure things are the same still, right? So, but then railways are also waking up, and then I'm helping them reduce the noise in railways as well. Okay, but because we are exporting the European market, we have to adhere to the pass-by noise levels. Okay, and now India also the government has put, the Central Pollution Control Board has also put the limits. If somebody wants to sell a car or an automobile in India, they have to satisfy the vehicle pass by noise levels. We have it as a regulation for the automobiles. We do not have it for the railways. We are, as I speak, we are working on it, and for the airport noise it is also going to come up, okay, because of the fact that this would lead to a high level of human discomfort, diseases and all that stuff. So, yeah, rightly said, what are the sources of noise pollution in India? Rail, road, air and machinery noise, construction equipment, firecrackers. You will recall earlier when we are having too frequent power failure in our country, and if you have been to places like Palika Bazaar in Delhi's Connaught Place, okay, there used to be gensets outside every shop, and they were not controlled and they would be making noise. I don't know if you have experienced that. Okay, everywhere, when of course now in our country power situation has improved, we do not have frequent power failures, but imagine if all those gensets made noise and how irritating it would be. But fortunately the Central Pollution Control Board has stepped in and they have mandated what is the noise level radiated by such gensets, okay, and I'll tell you about those standards also, and I just told you earlier also what are the standards for the firecrackers. So in India some levels are in place and some we are working on. So if you can go to the CPCB website, you will see the exact values, and these are all Gazette notifications. So it is mandatory that we adhere to these limits, or you could be fined, okay, you could be put in jail. Okay, let me tell you again, because this is being recorded, let me tell you, the district magistrate or the police superintendent are empowered to follow this, okay, but then this got sidelined because some community and some government, state governments told during this period, because they said from 10 o'clock to 6 p.m. there should not be any loud public broadcasting of any sound, okay, no public functions after 10 in the night to 6 in the morning. But there are some festivals, some governments made it, let's make it 10 to 12, and that is how it became diluted. But the Lordship of Calcutta High Court was the first person to implement this very strictly, okay, and so I know this for a fact that we stay in a campus, our campus is quiet, but we have a festival in Bengal called as Durga Puja, okay, and during Navratri, and let me tell you, I mean students, kids have exams, but there will be loudspeakers blasting around the boundary, and I am sure Professor Bolton the other day when he visited us, you could also hear that. Okay, so this is what is the state of affairs. Okay, if the police and the administration did their job, this should not happen. But laws are in place, let me tell you, laws are in place. Noise rules for PA system 2000. So now let us become a little technical. How do you quantify this stuff? So I don't know, those of you who visited my lab yesterday, I don't know if you have noticed that I had put in small sound level meter, and then you could see this pressure fluctuation on an oscilloscope while you were talking. So this could be calibrated and you can see the decibel values also. But if I was to get a single number out of this, because a meter is an RMS whole meter, so the very first definition of this L equivalent T is an equivalent continuous level, that constant level in dBA lasting for a duration T, which has the same acoustic energy as the given event. And by definition, sound exposure level is that duration there is only 1 second. For 1 second, whatever is the average level is the SEL, sound exposure level. But when I say equivalent duration T is something which I can define based on my requirements. Okay, and these terminologies are available in ISO 1999. Okay, so and once I have such a waveform here, I can always integrate and to find out whatever I need. So, if you look back to this equation, if this t is 1 second, it becomes an SCL. Otherwise, somebody may say, what is the 5-hour equivalent of this sound? So, you have to put your sound level meter on for 5 hours and integrate and so on. So nowadays in the airports, you will see continuous noise monitoring terminals, NMTs, noise monitoring terminals. You can define a period, and then they will data log it, find out a single number, and even store it in a database. And then it is right now as I speak, it is being installed in Bombay Airport, and then you have an NMTs close to the runways, so that people are recording these values with traffic density, what is the level high, and so on. And I do not know the reasons. If you ever have been to Delhi IIT, Delhi IIT comes right on the flight path of all the international flights coming down to Indira Gandhi Airport, and in the middle of the night you wake up because of a large flight aircraft coming down, and mostly all the international flights either land or take off in the middle of the night. I don't know the reason why. We have to find out the aviation guys what is the reason behind that, but it has to do something with the taxes perhaps. Okay, so the exposure level are pretty high, and that is why perhaps one is we try to move away from cities. Bombay is going to come up with a new airport in Navi Bombay. I do not know whether it is because of noise or because of the land and so on, but this could help. But once airports come up, community grows around the airport. So after a decade or so, same thing is going to happen. But then going back to my first slide, communities are prospering and growing, so things are happening. Okay, if you had been to villages, 20 years ago or 30 years ago, they are so quiet. Not anymore. You have movie theaters and villages nowadays, right? So things are happening. So that's a good sign, but fine, you progress, but please keep your noise under control. So what is this? So to calculate everything, all you require is the time history of the sound pressure level, and rest all you can do it by an integration. So in India, we have 4 zones: industrial area, commercial area, residential area, silence zone. I have a bad experience of this industrial area. I have been to many factories where particularly a lot of stamping operation is happening, as simple as making a beer bottle cap. Okay, stamping, tuck, 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 tuck. In the shop floor, the noise is terrible. Stamping operation happening. Okay, if you have been to any textile mill, spinning of these bobbins, okay, so noisy. If you have been to a jute mill, workers are in a pitiable condition, okay, because of the noise levels. I hope nobody will hold me to this, but this is my personal observations. Okay, so the industrial area, of course, regulations are there. During the daytime, by daytime I mean 6 to 10 p.m. the level should be only 75. Night time it should be 70. Otherwise, you need to give hearing protectors to your workers. Okay, commercial area, residential area, silence zone, hospitals, there is a no horn sign, blast it. In our institute, we have a no horn sign in the academic area. Plus, I try to always follow that. But then I have seen my colleagues, boom, they think again sometimes horn means right of way. Okay. So, and these are things, your habits and practices will help you do that. So, standards are in place, not that we do not have standards in India. Regulations, I should not get into trouble saying all this, I hope. But that's my personal experience. So. And this is the noise limits as per Indian Standard 3028. You will see, depending on for a 2-wheeler, 3-wheeler, and what is the maximum noise limit as measured by a pass by noise level. And sometimes, I'll discuss on day after tomorrow when we do case studies. We do noise control on many automotive manufacturers. In fact, they drive all the way from Pune, from Jamshedpur, from Indore, and bring their trucks. So we do noise control, and we do pass by noise right here in Kharagpur. And we have a long stretch of road in the defense land where there's no public, and it's a quite flat land. And I do pass by noise measurements to see. I'll show you some photographs on Friday. Okay, so people have to adhere to this, and many times, if you look into automotive noise control, this radiated noise exhaust happens to be one of them. Okay, I'll tell you a small story about that later on. And then this is the noise standard for the firecrackers. The manufacturer sailor is there are two ways of quantifying the firecracker generating noise. One is 125 decibel in the A scale under the impulsive weighting, or 145 decibel in the C scale. C scale is when you have a little higher noise levels. There is a C weighting, the equal loudness contour, unlike the A weighting, which is at 40 phones. This is at a little higher. And for higher noise level, C weighting is used, and that's what is given in the standard. But today in the industries, everybody is following the A weighting. That's good enough. But so any manufacturer of a firecracker has to ensure that their firecrackers should not produce so much of noise at a distance of 4 meters from the point which is burst, and this is measured on a hard floor. Okay, but you would have seen some of these bombs, where the people put everything in series, Fatka bomb and whatever. Okay, I forget the local name for it. Yeah, Chinese Chatai bomb. Okay, so N is the number of crackers joined together, so one has to be careful about that. And the measurement should be done on a hard concrete floor of 5 meter diameter, and measurements must be done by an approved sound level meter. I know for a fact, I get to hear the story from a manufacturer of a prominent sound level meter company, that suddenly they had a massive order of sound level meters from the Indian police. Okay, and once the Indian police called me to teach them noise control. Okay, and basically how to use a sound level meter, but I will not tell what happened beyond that, but that's the story. Okay. Again, noise limits for generator sets. Today you would see the large generator sets come with some sort of a protection device, usually in the form of an enclosure, and there are only few exceptions. For the case of defense establishments, they are exempted because of criticality of the requirements, and they do it in remote areas, etc. But I will not read into this. But this enclosure must have an insertion loss of 25 decibels, and if you put any exhaust muffler, it must have a minimum insertion loss of 25 decibels, and depending on the power of the DG sets, it could only have so much of dBA as measured, and things will be peaceful. Okay. And another thing this pollution control board is looking into is noise labeling of products. Today, if you go to a market and buy an electrical heater, or you would specify, I want a 1000 watt heater, or I want a 2000 watt heater. Okay, same is true. So one is power, and another is pressure. Okay, I will relate this to, say, maybe thermal energy, or thermal or electrical energy. So if I had a heater in this room, what would happen? The temperature would increase, right? If I switched on the heater, and assuming that this room was all sealed, it was adiabatic, and so on, thermally insulated, the temperature would rise. Okay. But if I opened a door, temperature would fall depending on the ambient and so on. But the power of this electrical heat is never going to change. Right? With that same analogy, if I have sound power of a machinery known, its SPL is going to change, you know by now, depending on where you measure it, at what distance you measure it, what kind of field condition you are measuring it, but the sound power would not change. Right? So, instead of measuring the sound pressure level of a machinery at a given distance in a given condition, it would be better off if I knew the sound power of that machinery. I will tell I will use a 100 watt or 100 dB sound power level ceiling fan or a blower and so on. So, that is inherent to that. So, if I can specify, suppose today I want to buy a refrigerator for my kitchen, and I would say the sound power of that refrigerator should be only 60 dB. By the way, we all talked about SPL as 20 log 10 of PRMS by P reference, where for air P reference is 2 × 10⁻⁵ Pascal. Similarly, sound power level is given by 10 log 10 of W by W reference, where W reference is 10⁻⁻12 watt. Okay, please make a note of it. And SIL, sound intensity level, also in decibel scale. These are all in decibel scale. 10 log to the base 10 of I by I reference, and I reference 10⁻⁻12 watt per meter square. This is again decibels. So, if I could find out or label a product in terms of SWL, it is good. I know whether one is quieter for sure or not, because SPL would change with the distance, with the environment and so on, but SWL is not going to change. Okay. And you all know how to measure SWL of a product. You can multiply the normal intensity and the corresponding area and sum them up and get SWL. Other methods of SWL by comparison method with the reference source, measuring the SPL and hemianechoic chamber, etc. Okay. So, such exercises are being taken by Indian industries to label some of their products. It has not been mandated yet, but it will come, that when you buy a genset or when you buy a refrigerator, its SWL would also be stamped, okay, and that would make everybody's life easier. Right? Otherwise, what happens? I will again I will tell you, in many noise control measures, particularly in automobiles, we would have put some material here and there, below the mudguard, etc. It is fine to satisfy the pass-by test when the inspectors are doing the certification test, but the first time it goes to the service station, the mechanics remove all those materials. Sir, ये मैला हो गया, निकाल दीजिए, जरूरत नहीं है, misuse. They do not never put it back, and your SPL level goes up. So, those are issues also, okay, because there is no periodic checking like we have the emission checks. There is a big story regarding the emission checks as well. Similarly, imagine if we had an pass-by noise level checks for vehicles, things would have been easier. Now, next question is, what is the permissible human exposure limits? And that is the question everybody asks. So, there are certain international standards. The OSA standard in the USA says a person for an 8-hour period must not be exposed to more than 90 dBA. And what happens, for every 3 dB increase in A-weighted sound level, the exposure time should be reduced by half. So, if the exposure time has increased to 93. Your worker has to be exposed to 93 dBA. So, please ask him to only be exposed for a duration of 4 hours, okay, and that is how it goes. Okay. So, if it is 140 dBA, you can imagine what I am talking about here. Okay. And so, India has adopted this international limit of 90 dBA during an 8-hour shift for industrial workers. Okay. But if you ever have sat in the cab of an Indian engine railroad locomotive, things are different. Okay. So, that is why we put extra protection, ear protection. Okay. Exposure is very bad. So, to monitor this, there are instruments available which you could wear. It is a personal noise dose meter. It will tell you what dose you have been exposed to in the period you have been working, and these are clip-on types dose meters, which has a microphone and then it has an integration stuff there inside it. Okay. So, this is the noise dose is calculated by this equation here, C1 by T1 plus C2 by T2 and so on, where Ci is the total actual time of exposure at a specified noise level. Ti is the total time of permissible noise exposure at that noise level. Okay. I'll explain this through a numerical. So, let us look into this. The operator on a noisy drilling factory needs to be protected from overexposure to the workstation noise by rotation of duties among the operators. The operator's ear level noise is 93 dBA noise during the drill machine and 84 dBA on an alternate work machine. What is the maximum duration during an 8-hour shift that a worker can operate the drilling machine? So, let us see. Let the worker operate for machine for X hours, then from the table of non-noise exposure limits, if it is 93, this table comes to 4 hours, and then if it is something else I do not know, because 84. Okay. So, this becomes 8 minus X, I do not know the time, out of 8 hours X is left, and then now we have 84. So, for 84, what is the permissible limit? Yeah, you reduce it, so it will increase. Okay. So, noise will be less, 87 minus 83 will be 84. So, your noise level is reduced, so your time would increase, 16 would become 32. So, if you plug that in here, so the exposure, if the operator is working for 4 hours at 93 dBA, another 3.43 hours, he or she can be exposed to 84 dB, and then that would be fulfilling his noise dose requirements as per OSA standard. So, that is how you can work around it. Right? Which one is the 100% noise dose, 100% noise dose. Okay. And then there are parameters wherein there are in different standards they say your total day night equivalent level by this exposure, because daytime would be 15 hours, would be from 7 to 2200 hours, and night time would be from 22 to 700 hours. So, you could do an integration and you see what is the overall day night equivalent level a person is subjected to, and that is as per the EPA standard. Okay. And there is an addition of 10 because of this actual nighttime noise is more disturbing. Okay, so with this kind of a background to the reasons why we have community noise or environmental noise, the significance or the fact that we have so many standards in our country, because we all are working on, in fact, I was a member of the National Committee on Noise Pollution, wherein we drafted some policies for the government, wherein we are trying to bring in awareness to the community, number one, educate them how to measure, and of course, as an engineer, I tell the clients how to reduce their product noise. Okay. So we do a lot of plant noise monitoring. This is a plant, in fact, this is very close to us at Kharagpur, where this is a steel plant where the air needs to be fed to the blast furnace, and there were blowers in that plant, 5 blowers in series, and I'll play some of the sounds later on in the lab. The noise levels were very, very high, okay, and workers were allowed to only go in after they put on a ear muff. And I'm sure today, if you go to any Indian factory, the safety limits, the safety regulations are strictly adhered to. You are not allowed to walk in without the goggles, safety shoes, gloves, and a ear muff where places are noisy. Okay, so we have to stick to that. And of course, they wanted a permanent solution, so we worked on an enclosure, wherein if you put an enclosure, the problems, it leads to another engineering problem. I may reduce the noise, but I may screw up the thermal system in that the temperature may increase, and the bearings may be exposed to high temperature, and that leads to another problem. So there are actually chillers in the intake exhaust silencer for those enclosures as well to cool the air. Yeah, this is a, if you can see here, this is a tractor wherein I designed a muffler which is now inside the tractor. Okay, there are two things here. Of course, now many companies do that. One is this big muffler is not sticking out, so the driver's eyesight, in this case I happen to be the driver there, and this was about 15 years ago. I was little lean then, okay, and that the driver's view of the front is not blocked, okay. Another is doing a better job of the putting the muffler inside. I could reduce the pass-by noise so that they could pass the legislative requirements of this pass-by noise for the tractor. And this is by a software tech muff. This morning, Professor Bolton was mentioning about this transfer matrix approach to find out the transmission loss, etc. of these mufflers, and that's a one-dimensional theory. And if you look at the handbooks, you will get the matrices of different muffler elements. You could perhaps multiply them and make your one-dimensional muffler analysis, and it works pretty well. Okay. Circular duct silencers are used in many of the floor cases wherein the pressure are very low, and these are all people use in the industry to reduce the environmental noise pollution. For example, another issue is steam ejecting out of a pipeline, because steam is generated from a boiler. I cannot shut the boiler. Boiler is always on, and if the steam pressure builds up, the safety valves will open up and they'll make a hissing noise, which and these are irritating. They add to the environmental noise. So we have to design vent silencers wherein we can reduce such exhaust noises because of the steam exhaust at high temperature and high flow. Okay. Well, if nothing works, please put in ear muffs and plugs and so on. These are just some views, which I had done some work somewhere. And ventilation silence, barrier walls. This is a transformer housing, panel enclosures. These are all to reduce the community noise. In fact, we did a project for the Steel Authority of India, wherein they were looking at, of course, the steel companies will look into ways by which they can sell more steel. But then they came up with an idea that in Delhi, big flyovers and metros are coming up. Could you work on steel barriers to reduce this noise being radiated out of these highways? So the way they did was, they made this high barriers about 12 to 15 feet in height, and they had lined it with fiberglass, and we were just seeing the noise reduction. And as a cool way to do it, I blast it with a random noise in a loudspeaker, measure in front of it, measure behind it, and this we are testing at that site at RDCS in Ranchi a few years ago. Okay. Because people are aware of things, how to reduce the community noise. Okay. Processes will go on, and Increase in noise is a sign of growing of civilization. If you are, and that's what I tell my colleagues in the department. If we are consuming more electrical power, it is good for us. That means we are progressing. Okay. Okay, but we are not wasting. Well, there will be leakage in any system. That's fine. But if we are consuming, we are producing, and that's a form of energy. Thermodynamically speaking, if energy is coming into the system meaning the community, we are doing some useful work, right? So please do not stop anybody if he is asking you sources of energy. Okay. So this is a question which we will discuss tonight in a party maybe, but okay. So these are the materials which are used for noise control and combination. So I will not discuss this anymore, but then people use barriers in the blankets in the industry. For example, in press shops, you will see these barriers hanging to reduce in something sound wave goes in, it gets trapped, it gets absorbed, so to reduce the noise. Okay. So there is no end to your imagination to apply noise control. Okay. There are many cheap ways. Professor Bolton was mentioning about those shoddies. Okay. Very cheap. Natural fibers, very cheap. Tomorrow Dr. Fatima is going to talk about natural fibers. Okay. How cheaply we can reduce noise and product noise could be reduced. Okay. A good engineer, in India we call what is a jugaad technology. It's not jugaad, but it's frugal engineering. We can, jugaad is a local term. Quick fix, it works. So as long as I can cheaply solve a problem, I am doing good. Thank you all. Any questions? I would happy to take them.
Are there any nations that are following the concept of stamped SWM now?
That's a good question. I do not have a definite answer to that. You want to take? Do they have a stamped sound power level on their product? I have a lawnmower in my house. It came from Australia. I say it's stamped 75 dBA somewhere. I don't know. Maybe it's in Australia. It is there.
There are some things that I think are labeled.
Yeah.
And some things are shown in sounds.
Okay.
And tires in Europe, I think, now have a noise rating.
I see.
Based on the half-life test, but I'm not sure. So in the U.S., there's certainly no uniform noise
Right.
labeling.
Well, that would be a good concept if everybody started to do that. Yeah.
So I was thinking about the idea of sound power versus sound pressure level, like the stamping that is to be done.
Right.
So, for example, you said that if it is in a space and the space is not enclosed completely, if there are spaces from which the pressure can go, then the dB will decrease, I think.
The sound pressure level would change depending on the field and depending on the distance, but the power would not change. That's what I wanted to say.
So then do we have like products that are wherein you mention that what is the kind of field that this is compatible with? Like for example, if it is making a certain level of noise, and if it is making a certain level of noise in an open field, then certainly the pressure level will be less, right?
Yes.
And so the noise produced will be comparatively lesser. So do the products also consider where it would be used? I mean, like a refrigerator would be in a kitchen, or
right. See, to answer that question, I'll take the cue from your question regarding the refrigerator. If a manufacturer is comparing their refrigerator with another competitor's refrigerator, they have a standard. For example, it's in a room, it's in a reverberant room against a hard wall,
right,
and then do a measurement. So sometimes for comparison's sake, they use a certain condition, which is same everywhere.
okay.
But sometimes people cheat. So why is so much aircraft certification conducted in North Africa?
I see.
On nice sandy
questions? Okay, thank you.